when I study thermodynamics, one of the subjects I really enjoy looking at is the study of phase transformations and drawing a phase diagram. I'm not sure why that gets me so interested. It seems like a weird thing to get excited about. But somehow going from a table of thermodynamic data like this to be able to draw a full phase diagram of a system, that's a cool thing for me. I like it a lot. It may be that this relates to the fact that some of my favorite examples of this are mineralogical systems from geology, systems where a single chemical composition will correspond to multiple crystal structures of that system, and the history of the rocks that have a given type of substance, a given crystal structure, can be deduced by looking at which crystal structure is stable under what circumstances. This probably dates back to my mother having gone to grad school in geology and geeking out about rocks when we go on family vacations. But whatever it is, I like the subject. It's a big one. I've made up three make-believe substances, or rather three make-believe crystal structures of the same substance, the same chemical substance, three minerals that have the same chemical composition, and they're called anarite, alundite, and isildite. And what I want to do eventually is construct a full phase diagram, at least an approximate phase diagram for this system. See what temperatures and pressures each one of these phases, each one of these crystal structures is stable under. Now, that's a long process. So let me tell you where we're going with this. I'm going to make a first video where I just go and look at the data, how to interpret this data, talk about some subtleties in notation that are super confusing until you really think about it hard, and do the basic calculations, not for the full phase diagram, but just to figure out at what temperatures each one of these phases is the stable phase at standard atmospheric pressure. Okay, so that's going to be the first video. Second video I'm going to do, we'll talk about some subtleties involved in all this, some of the nitty-gritty details, places where our approximations actually aren't that good and how we can make them better. And then I'll do a third video where I go back to the simple approximations, but then I'll build on our results from the first video and construct the full phase diagram over a range of temperatures and pressures for this system. All right, that's the plan. So for now, I just want to talk about how we interpret this data, how we do stuff with it. In a standard table of thermodynamic information, this is only a subset of it. In this table, I've got a column for the Gibbs free energy of formation per mole. These tables are usually written per mole. All the quantities are per mole at standard temperature and pressure, 298 Kelvin and 101,000 pascals, 1 atmosphere of pressure, 1.01 bar, 10 to the 5th pascals of pressure. So that's what this data is. I've got a column of Gibbs free energy of formation in kilojoules, of standard entropies in joules per Kelvin, of specific heats in joules per Kelvin, and volumes in centimeters cubed. And again, that's centimeters cubed per mole of the substance. So we've got this data, and the main tool we're going to use to analyze phases is Gibbs free energy. Here's the thermodynamic identity for Gibbs free energy. Tiny change in Gibbs free energy is equal to minus entropy times change in temperature plus volume times change in pressure. That's our core identity for Gibbs free energy. It's the reason that Gibbs free energy is what we want to use, because Gibbs free energy is a natural function of temperature and pressure, which are intensive variables, variables that describe a substance or an environment rather than things like volume that describes an actual object or something, the size of a thing. So this is our this is our thermodynamic identity that we're going to focus on. And as I hope you know, the stable form of a substance is the stable form among different phases will always be the phase that has the lowest Gibbs free energy among the options available to it. So in this case, I look at these, the most negative of these three numbers is isildite, negative 2245.7 kilojoules. It's a little lower than the others, so isildite is the stable form at standard temperature and pressure. But that won't always be the case. Here's the gist of it. The general idea goes something like this. Based on the thermodynamic identity, if I hold the pressure constant, I can, physicist talk here, divide by dt. I can deduce from this that the derivative dg dt at constant pressure is negative s. The entropy is the negative of the slope of the Gibbs free energy versus temperature graph. And what's that mean? That means that if I were to draw a graph of, just to give the gist of it, here's temperature, here's Gibbs free energy. If I were to draw a graph for, say, the, I'll do the Isolde state first. For the Isolde state, I would find its, here's its Gibbs free energy initially, some initial Gibbs free energy for it, and it's got an entropy that is something like this, is 94.4, that's a slope, so negative, it'll be a negative slope with that slope. I don't know, it's going to be some line that looks kind of like this. Okay, so that would be a rough graph. Now this is assuming that that's a constant, which it totally isn't, but just to get the gist of it, I can see that Gibbs free energy will change with temperature based on the negative of the entropy, it being the slope. And this is for Isolde. And the whole idea of this, the idea of phase transformations, is that if I then looked at Anarite, if I looked at Anarite, that has a different Gibbs free energy. You'll notice it's a little bit less negative, so it's a little bit more positive. I'd have my Anarite here. I don't know where to put this. Anarite here, and its entropy is different. So it has a different slope. In fact, it's a smaller number, so it has a lower slope. Roughly speaking, it's going to have a lower slope, a flatter slope that's going to look, oh, that's too flat, but whatever, look like this. And you can see then that there is a point somewhere here that we'll call temperature, Anarite Isolde. And that's the temperature where Anarite's Gibbs free energy is now lower than Isolde's. That's the transition temperature between the two. And we could do the same thing for Ellendite, right? Ellendite has an even higher Gibbs free energy at standard temperature and pressure. So Ellendite might be up here, Ellendite up here, but it also has the highest entropy of any of them. So it has the steepest negative slope. And so, over exaggerating just to give the idea, it's going to go something like that. And so I expect to find over here some temperature. I'll call it the temperature of Isoldite and Ellendite, where we find that Ellendite becomes the stable form. That's the idea. And of course, this is a very, very rough graph because I know that entropy isn't constant. The slope won't be constant as I change temperature. I know that this is just a rough idea, but this is the gist of it. So our goal, I guess technically, there is another point that could be interesting, right? There is the Anarite Ellendite temperature, TAE. That is a transition where those two trade which one's higher or lower, but at standard pressure, that won't matter. So that's the gist of this. That's the general idea of how you look at these calculations of what we're going to do. Our goal is going to be to say Isoldite's lowest at standard temperature and pressure. I want to find these two temperatures, the AI and the IE temperatures, because those are the boundaries between the different phases, the boundaries where those become useful. So as I said down here, my goal is to find the temperature where Anarite and Isoldite have equal Gibbs free energies. And similarly, the temperature where Isoldite and Ellendite have equal Gibbs free energies. And we'll see what shapes up that way. We'll figure this out. That's our plan. Okay, how do we do that? How do we translate from this table into something that will let us do a calculation, that will actually do something? Well, morally speaking, what I would kind of like to do is just take the thermodynamic identity, say dP is 0 because I'm doing constant pressure. So dP is 0, and I want to say, well, I want to say that change the infinitesimal thing into a delta. Delta G equals minus S delta T. That's kind of what I want to do, but that's dangerous. It turns out there are a few things going on here. One of them is that the entropy, we'll talk in the second video about this, the entropy is really not constant with temperature. Here, look, the ds is dq over t, it's the specific heat divided by temperature, dt. That's going to add up. That temperature changes, this automatically changes. So I'm already nervous about treating this as a constant and doing this. The other thing that makes me worried about this that I want to comment on is that delta G is one of the most horrifically ambiguous notations. One of the most horrifically ambiguous notations in this study that you'll ever run into. Because, let me just point this out. What does delta G mean? Because it can mean totally different things depending on the context. One thing it could mean would be delta G is equal to, for example, the Gibbs free energy of, say, anorite at temperature T final minus the Gibbs free energy of anorite at temperature T initial. The difference in Gibbs free energy of a single substance at two different temperatures. That's one thing it could mean. It might also mean the Gibbs free energy of anorite minus, maybe at temperature T, minus the Gibbs free energy of isoldite at temperature T. It might mean that. Or, making it even more confusing, it might be the delta G of formation for this table. So the Gibbs free energy of formation. And that's horrifically confusing. We've got three different things that we're going to call delta G along the way, that we might be tempted to call delta G along the way. And that's just not sustainable. That does not work for these sorts of things. What are we going to do to make sense of this? Here's my plan. And the notation is not good for this. It's just not. What I'm going to do, so delta G of formation, that notation delta G of formation is related to the definition of this. It's making it clear that you're defining this with relation to 0 points of Gibbs free energy chosen for each of the individual elements that went into it, blah, 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 blah. It's an important notation, but it's confusing for these calculations. So here's what I'm going to do. My standard thing is going to be that I am going to replace, once I'm doing calculations, I'm going to say, for example, the delta G of formation of anorite. When I want to use this in a calculation, I'm just going to call this G anorite of T naught. G anorite at my given temperature. Oh, I hope that's visible. There's a little reflection from the window there. Hopefully it's not too bad. So I'm going to just write it as G anorite of temperature T naught. I think that's the way I'll usually write that out. So I'll try to be consistent about that. I might sometimes write it as G anorite naught or something. I'll see if I ever fall into that. Sometimes that's tempting for me. But that's one thing I'm going to do. Another thing that's going to get rid of this delta G of formation thing. I'll just write that as my initial value of a given substance. Another thing I'm going to do, just to be clear about it, is when I'm talking about the difference in Gibbs free energy between two different phases, I'm going to label my delta to make that clear. I'm going to say that delta subscript AIG is going to mean GA minus GI. That's what I mean by delta sub AI. So the subscript on delta means, hey, this is a difference between these two phases. That's not at all a standard notation, but it's going to help me keep track of what's going on. And finally, the final type of delta thing that comes up along the way, if I say, I guess if I have just a delta G equals G of T minus G of T naught or something, that's going to come up sometimes too. The difference, I guess I should say delta GA, this is all for one particular phase. I'll probably use that notation occasionally, but usually, so if I put a delta without any subscript, I'll probably mean that to mean a difference between two different temperatures of the same Gibbs free energy. But usually, I'm going to try to remember to just write this out explicitly rather than using delta G as a shorthand, just because it is confusing. So that's how I'm going to try to make the notation less ambiguous. to make it clearer what I'm doing at any given point. All right, those are all the preliminaries we need. What I want to do now is to actually calculate what that temperature is of our first phase transition, this anarite-isildite phase transition. I want to work out that temperature. Let's do it. Okay, so I guess what I really need then, to be able to say G anarite equals G isildite at some given temperature, I need to have an equation for G anarite, right? Or at least I'd like to. So I'm going to use my thermodynamic identity with pressure held constant, so dP is 0. And I'm going to say that the integral dG from my reference temperature to some final temperature is going to be the integral of negative S dt from my reference temperature to my final temperature. That's my plan. That's what I want to do. And this integral on the left is just going to, it's just an integral. I'm going to say that this means this is G, and so I'll look at anarite to begin with, just to have an equation, a specific equation for it. This tells me that G anarite of T minus G anarite of T naught equals this thing. I want to say that it's equal to just minus S times T minus T naught, minus S times delta T. I want to say that. I'm not going to. I'm going to say minus integral from T naught to T of SA dt, because I know that entropy changes a lot from one temperature to the next. I know it does. But I have this equation. This is handy. I guess I could rewrite this. The one thing I will do is rewrite this to say G anarite of temperature equals G anarite of reference temperature T naught minus that integral of S dt, S anarite dt from T naught to T. I've got that. I can obviously do the same thing for any other element. So I'm going to do the same thing. I'm not doing that integral yet, remember. I'm going to do the same thing for isildite and get the same result, basically, right? G isildite of T equals G isildite of T naught minus the integral from T naught to T of S isildite dt. That gets me what I need. That's the same idea there. And it turns out, here's the approximation we're going to make. I know that the entropies are changing a lot with temperature. But I'm optimistic that both entropies, as temperature rises, the entropy will rise. I'm optimistic that they're going to rise in similar ways. So that even as they both rise, I'm optimistic, I'm crossing my fingers, that the difference between those entropies is going to stay closer to constant as that goes up. It's a little ambiguous. We'll talk about it next time, but that's what I'm going to do to make this approximation a little better. What I'm going to do is this. I'm going to set GA equal to GI. So at my temperature T, at my special temperature TAI, I'm going to set those equal. And so when I do that, I will find, so GA of temperature T AI equals GI of temperature T AI. When I set those equal, that tells me I'm going to set these two things equal. That tells me that GA of T naught minus the integral of SA dt from T naught to T AI, that should equal GI of T naught minus the integral from T naught to T AI of SI dt. Okay, I'm getting there, I promise. And at this point, I can separate these things out. I can subtract, so the left-hand side becomes GA of T naught minus GI of T naught. And the right-hand side is going to become, well, that integral comes over there, and these are both integrals dt with the same limits. I can put stuff inside. This is going to become the integral from T naught to T AI of SA minus SI dt. I'm going to treat that as constant. I'm going to approximate that difference in S as constant. So let me write this down in terms of our notation. This means that delta AI G of T naught equals the integral from T naught to T AI of delta AI of S dt. And if we approximate that difference in entropies as constant, then we can do this integral easily as an approximation. And let's see where that takes us. I'm going to leave that whole section on the left right there. I'm going to erase here. Now that I have my gist of it. Okay. So I'm going to erase this stuff. And I'm going to treat this as a constant. So I'll write that down. Approximate delta AI S as constant. And so that tells me then that delta AIG of T naught is approximately equal to a constant pulls out of the integral, delta AIS times, and that's just an integral dt. So that's times T AI minus T naught. That's what I get when I do this, when I do an integral of a constant, right? I just get the delta T, the difference in temperatures over there. And at this point, my goal, my entire goal in all of this is to solve for that unknown temperature. And all these other things are being treated as constants. I can just do that at this point. I can just solve for temperature. I can, let's see what I do. I'll divide by this and then add T naught. I'll find that T AI, that phase boundary, is equal to T naught plus delta AI of G at T naught. That's my reference temperature, my reference difference here, divided by delta AI of S. And again, at temperature T naught, basically. That is my reference temperature. I'm treating this as constant, that these are constants. And I can put this in. What do I have? My T naught is 298 Kelvin, 0.15, I know, but who cares? This data is not going to be precise enough. I'm making lots of approximations. The 0.15 is completely negligible here. 298 Kelvin, I could probably call this 300 Kelvin and be pretty close. 200 Kelvin plus my difference in G between anarite and iseldite, A minus I, looks like it is positive 0.3 kilojoules. That's my difference between these two, this minus this. And my difference in entropies, again, A minus I, this minus this, if that were 94.5, that would be 5 joules per Kelvin. It's not, so it must be negative 4.9 joules per Kelvin. That's what we've got. That should be what we have. And when I work this out, this comes out to be 298 Kelvin, and then minus, when I do that division, minus 61 Kelvin, because this is kilojoules, so that becomes 300 joules in the numerator. 300 over 5 is about 60. That seems right. So this is approximately 298 minus 61 gives me 237 Kelvin. So there's my answer for that first temperature that I had, the TAI. I can use this same result, the same mathematical form, for the iseldite-ellendite thing, because the arguments would be exactly the same, right? They would just be relabeling which was which. For the iseldite-ellendite transformation, I'll find that T iseldite-ellendite is equal to same T naught, our reference temperature, plus delta IE G at reference temperature divided by delta IE of entropy, again at our reference temperature. And I can put those numbers in. Again, 298 Kelvin plus Okay, I minus E. This minus this is going to be negative, this minus this, negative 2.2. Negative 2.2 kilojoules, 2,200 joules, divided by delta IE. This minus this gives me negative 3.7, negative 3.7 joules per Kelvin. Check my notes to make sure I didn't just screw that up. Where did I put it? Where did I put it? So yeah, cool. All right, and when I put that together, 298 Kelvin plus, and this one's going to be plus because the negative over negative gives me a positive. When I put that together, I got plus 595 Kelvin. So this gives me a phase transition temperature estimate that is 893, yeah, 893 Kelvin. So there we have it. I have found those phase transition temperatures along the way, and we can then, knowing those two temperatures, we can then sketch out a picture of what that phase structure looks like. Let me sketch it out for you really quick. We're going to find, oh, I've just erased part of that. We're going to find, here's my temperatures, and here is temperature 0. So if we've got room temperature here of, say, 298 Kelvin, then our boundaries are at 237 Kelvin. So somewhere like here, 237 Kelvin, and way up here, 893 Kelvin. We have this boundary. Down here, Anarite is the preferred phase. In the middle section, Iseldite is preferred. And way up high, Ellendite is our preferred phase at very high temperature. So that's what we have, that's what we've come up with in this calculation, and I've spent plenty of time, way too much time already doing this, but this is how you sketch the phase structure at constant pressure of a substance, of a system like this. You just look for where you set the two G's equal. Find your specific temperature where those two G's are equal. You have four functions for Gibbs free energy as a function of your initial Gibbs free energy and an integral of entropy. And the difference, setting it up so you're doing an integral of the difference of entropies, is a little bit more reliable than integrating and then pretending that each entropy is a constant on its own. It's still not perfectly constant. That's what the next video is going to be. And we haven't talked at all about changes in pressure. That's what the third video is going to be. But this, I hope, gives you a sense of how this works. You take data from the thermodynamic table, you take the Gibbs free energy thermodynamic identity, and you put that together to set the Gibbs free energies equal to find those phase boundaries. And that's where we go.